Our first speaker today is Gabriela Limonta. Gabriela is researcher in CyberSecurity Research group at Nokia Bell Labs. She specializes in using trusted computing technologies to create Trustworthy Telco Cloud. When she's not doing this, she's probably knitting and enjoying Netflix. It's her second time on Code Dive. Last year, she delivered a presentation about working with trusted hardware in practice. Today, she will deliver a presentation, What does it mean to trust your boot process? Please give a warm welcome to Gabriela.
Hello, everyone. Thank you. I was here last year. I've been working with trusted computing technologies for about 2 years now. That's me. I'm both a computer and communications engineer, so trust me. Double. No, I'm kidding. But yeah, I think the things about me were already said. So, well, I work in trusted computing and I try to specialize in root cause analysis for safety critical systems. So you measure what's the state of your system and then you actually want to investigate, well, what went wrong. So that's the thing I'm interested in. And my free time, I'm usually knitting, running, or doing calligraphy. And clearly I can only draw letters because my art is not very good. Anyway, this all started because when I started working with trusted computing, I used machines. They would boot, so you power them on. You see grub at some point, and then you get your OS. This is pretty simple, right? Well, it turns out that whatever happens right at the beginning there between you press the button and you see your grub screen is actually quite important. It's the fundamental security of your platform. So that's the firmware. And firmware, let me tell you, it's everywhere. It's in your phones, it's in your hard drives, it's in your USB sticks, it's in your computer, wherever, if you can see it and has hardware, it probably has firmware. Anyway, the firmware stands here in the stack of things that run on your machine. First, you have your hardware. Then the firmware serves as this kind of middleman between the hardware and the operating system it provides. Abstracts away the hardware so that the software can actually do stuff with it. So it's a piece of code that initializes your hardware and it provides the abstractions to the higher level system. It can start your operating system. And it has the important functionality that it can actually restrict some privileged resources, like updating itself. So why do we care about firmware security? This is my favorite story. It's a bit old now, but it has it all. It has a three-letter agency from some country. So this came out with the Snowden revelations back in 2013, 2014. It turns out that the NSA was tampering with Cisco routers. They were flashing new firmware on them, tampered firmware, to get a backdoor into these devices. So Cisco didn't know that this was happening, and this is why I argue that firmware security is important. So I started wondering, now, how does the boot process work? Because fine, I understand it's important, there's something happening there, but I didn't really know why. So if anything you take from this lecture is, I just want to give you an overview of how different boot processes work, what we can do, what technology is there, so that we can somehow protect some of our platforms. So all errors in this slide in the interpretation of the standards for booting are mine, and bear with me. So in the beginning, there was the BIOS. It's this nice screen you get when you turn on your machine and you spam on the F2, escape, delete, whatever key your machine sets for entering the settings. And here you can configure your firmware. So BIOS is actually legacy code now. But the way it works, so you can still run machines in like legacy mode. So the way a BIOS machine boots is first, well, you turn it on. And the first thing that runs is the BIOS code, which is in read-only memory in the SPI flash. And then it goes through power on self-test. So that's usually when you turn on your machine and you hear the fan going, making some noises. It's actually enumerating, well, what can I see? What devices do I have? Let me initialize all of this and make sure that everything's working fine. And it sets up basic I/O. So your keyboard, make sure it's that your keyboard and your display works at least, so you can continue from there. And if there's any errors, it'll probably give you an indication. So if it has the video set up, it'll probably flash and say, hey, I have a problem with this. And if it has another problem and it can't display it, sometimes it actually makes really nice beep, 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 beep noises that you have to figure out. Then, once you've loaded the BIOS, you can read the parameters from CMOS, which is the, I can never remember what it stands for, but it's the metallized, oxidized, it's some flash memory. So this is basically where all the settings for your BIOS, so when you change the settings in this blue page with text, that's where these settings are written. So sometimes the BIOS code needs some extra parameters to initialize some disk or the network or something. It gets it from there. Another thing that it gets from the CMOS parameters is the boot order. So when you go into the machine and you change, oh, I want to boot from my USB stick so I can install my OS, and then you change it back to your hard drive. So then comes the selecting the boot device phase of boot. So it basically goes through all the boot options that you've enumerated in your BIOS, and it'll check for a master boot record in the disk or wherever it's booting from. And then there should be so the first partition should be a 512 megabyte bootloader, whose responsibility is just to find the next stage bootloader, and finally you get your Linux, hopefully. It might work a bit different in Windows, but disclaimer, I don't really use it, so details there might be a bit missed. So, as I said, BIOS is legacy code. It's pretty old. It was a de facto standard, but everyone had their own quirks to it because there wasn't really a standard, so in comes UEFI. So to highlight some of the difference between the two of them is that, well, in BIOS, you use this master boot record for enumerating the partitions on your disk, and then UEFI moves to the GUID partitioning tables. And the important thing from this is that you can actually boot from hard disks that are larger than 2 terabytes. So that's pretty cool. Then they actually, as I said, they defined a standard for booting. So there's a UEFI forum, which there's many companies in there defining what the standard should be. So there's some hopefully standardized behavior for UEFI. They introduced secure boot, which I will cover a bit later. And then the final important thing is, since they had more addressable space, it means we could get these pretty interfaces where you can actually use your mouse to click things. Anyway, with UEFI boot, things change a little bit, but they're still somewhat similar. So the first stage is the secure boot up. So in this part, you go to the initial boot block where the firmware, the first part of the firmware is, and you load this and you verify this. I'll explain how this verification happens a bit later on. And you make everything ready so that the pre-EFI initialization phase can start. And this is similar to the power on self-test that we had in BIOS. So it's going to go and enumerate, well, what can I see? What are the devices I can see? But it won't go and initialize them. It actually makes the whole environment ready so that the driver execution engine can run. And then this dude has a responsibility of going through the list and saying, okay, network interface card, I see you. You know what, go initialize yourself, then come back and tell me when you're done. So he's kind of like a boss. Goes, tells people, or tells components to initialize themselves and return back. So this actually makes it so that the code for initializing the devices attached to your computer is a bit decoupled from the firmware itself. So in BIOS, you actually had to put in the firmware how to initialize these devices. Now you can have these EFI drivers. So it's kind of cool. And then you again read there's some EFI variables where you can read the boot order from, and then you go and pick an appropriate boot device, and you try to boot from it. So you enter then what's called the transient system load. So in this phase, you have a transient bootloader from UEFI, which will search for the real bootloader in that partition you're booting from. And then you run the final bootloader, and you go into runtime. So once you go into runtime, UEFI, or most of UEFI is trashed or taken away, but they actually keep some runtime services that they offer the OS on top. So you can still modify some variables for UEFI. You can modify the firmware. So they provide this kind of interface to still do some operations towards the firmware. So that's nice. How do we trust this, the x86 architecture? So there's two options mainly, secure boot and measured boot. So with secure boot, the idea is that you verify each component that runs. You verify their digital signatures. You check that they're signed by a very good and trustworthy party. And if they are, you let them run. If they're not, you stop the boot process. So you start with the firmware, and now the boxes here are going to be a bit simplified just to go a bit faster. Anyway, you start by self-verifying the firmware. Okay, signature is correct, I can run it. Then you go and verify the signature for the bootloader. If it's correct, the bootloader can run. And then you go and verify the signature for the kernel. If it's good, it can run. And you can do that for the kernel modules as well, and it can run. Cool, you made it to runtime. If at some point there was a bad signature, somebody or some untrustworthy party signed some component, bam, you get a secure boot violation. So many people just go and turn it off. And to be honest, I don't have secure boot enabled in my machine. But let's take a look at how the PKI around this works. So there's 3 different databases that secure boot uses, and a top-level master platform key. So the platform key is created by the vendor of your machine, so the original equipment manufacturer. They create a key pair, and they store the public part on your firmware so you can verify stuff, and they keep the private part. So in my machine, you can actually go and check these through these runtime services from UEFI that I mentioned. Even though I have secure boot disabled, I can still see the variables with this information. So my platform key is from Lenovo. Well, that makes sense. My laptop is made by Lenovo. Then there's the Key Exchange Key database, or the KEK database. This database is a database of trusted certificates. So these are the people that are allowed to sign good things or to be trusted or trustworthy. So if I read my database, I have 2 keys. One of them is from Lenovo, and the other one is from Microsoft. In some machines, I'm told you can even find a key from Canonical, maybe these machines that come with Ubuntu pre-installed. I haven't seen one of these before, but it should be possible. And why this happens, it's because when UEFI was set up, Microsoft volunteered, hey, I can sign things, I can be a CA, I'm very trustworthy. And people said, well, sure, why not? So that's how it went. So then the interesting databases are DB and DBX. Very creative naming. So DB is a database for all the good things. So here you can store code signing certificates, signatures. So it's like a whitelist database of what things you're gonna let run on your machine. And in my machine, again, I have some keys. Well, I have more of them. I have 4 now. I have 2 of them from Lenovo and 2 of them from Microsoft. And then the DBX is like the revocation list. So if you have anything that becomes untrusted, or you know the signature of some malware you don't want your machine to run, or well, I should say the vendors, know some malware that they don't want your machine to run, then it goes into DBX. And I have a lot of them. I actually can't show all of them. It's like 70 of them. I honestly don't know what they are, but they're bad. Anyway, that is how you verify if something is trusted or not. So when you're booting, you search for it, you verify the signature against some key that is in the good database. And if this doesn't show in the bad database and it's well signed, cool, you can run. And well, if it's badly signed or you find it in the bad database, then you don't run. And now you might be wondering, hey, those were Microsoft keys, but I'm running Linux in my machine and I have enabled secure boot. What's going on there? So some of the Linux distros use this thing called shim, which is a very, very tiny bootloader that Microsoft agreed to sign. So what they do is Microsoft signs shim, which is a very dumb piece of code. It doesn't do much. It goes and calls grub. But one of the things it does is shim allows you to add extra keys for verification. So then the Linux distro people, so Fedora people, Debian people, whatever, they can put their keys and certificates into shim and somehow extend the validation there. Then shim can pass those keys to grub, and grub can continue verifying what comes next, so it can verify the kernel. So that's kind of cool. I must say, well, Microsoft signs these things, but fortunately, they're not the only ones reviewing it. So I like to think, well, there's at least that. So there is actually a cross-distro workforce group or something that reviews any binaries that you submit to Microsoft saying, hey, please, can you sign this because I want to boot from this. But you might still be feeling uneasy and thinking, well, I still don't like this. I don't like that I can only see Microsoft keys and I don't feel in control. And that's okay. You can actually go into the BIOS and click delete all the keys, and you can get rid of all those keys that you don't have the private part for. But your mileage may vary, because then you have to do the whole maintaining of the infrastructure. You have to put your own keys there, and then you have to sign the things that you're allowing. So in some situations, it might be worth it. In some other situations, well, I don't know. I'm not doing it for my machine. So it's a trade-off. You gotta see what works for you. I'm just showing there's these options. But I stand by, well, I always like to tell people that I think verifying signatures is not enough. I mean, it's cool that we do it, and we should do it, but it's definitely not enough. And to illustrate my point, I have another example attack, which I like. Well, I guess you shouldn't say you like an attack, but this is quite clever. So earlier this year, some researchers brought to light the fact that ASUS software had been hijacked. So if I explain this, when you have an ASUS laptop, it comes with this live update tool, which is one of these tools that allows you to update the firmware, update your drivers, install applications from ASUS. All cool. So then this live update tool, when it downloads a new update, it'll check, well, is the update correctly signed by one of ASUS's certificates? Yes, no. If yes, cool, let's go ahead. So what happened is that some attackers actually managed to compromise some of the certificates. Okay, they were some old certificates, and they managed to sign some malware and stick it into people. So people would boot up, see their computers, live update tool, critical, please update me. And we always tell people, if you see an update, you gotta update, you gotta keep your systems up to date. So what does the user go and do? Update. Then you get your perfectly signed good malware. And well, the thing is, we don't really know what the malware did. It was a very, very highly targeted attack. So when you downloaded the malware, it would check your MAC address, and it would have a list, and it'll check, are you on the list? If you're on the list, it would talk to the command and control center and get a second payload and run it. But by the time researchers got to this, the command and control center was down, so they don't really know what was happening to the infected machines. So if you weren't on the list, you're fine. Nothing bad happened to your machine, but you still had that backdoor there because it stayed silent and dormant. So I argue that it's not enough code signing, because then code signing also comes with a problem, or complication, not a problem. These were all certificates, which means revocation becomes difficult when you start. So if you have these certificates that you use to sign code, and they're a bit old, and they get compromised, how do you revoke those without having to update or revoke all the other code that you already signed with them that was good code? So it's a bit, I understand that it's a bit complicated. But that's why I'm of the opinion that you verify, you trust or you sign, but you also verify with measurements. So if verifying is not enough, as I'm telling you, and you all clearly believe me, because I don't see anyone going, oh no, she's wrong. So what do we do now? And let me introduce you to measured boot. Or the TPM, actually. I can't follow my own slides. Anyway, the TPM is this little tamper-proof chip that comes in many server-class hardwares and laptops. There's one in that little laptop there. Some phones have a version of this. And it has some very nice features. So it has the idea of a permanent identity. So it has a pair of keys, a public-private key pair, of which you can only read the public key. The private key stays on the chip to do operations on the chip. So you have one key for encryption, decryption, and another key for signing. A nice thing about the signing key is that it can only sign things that were generated inside the chip that follow a certain structure. So you can, if you get information out of the chip, you can guarantee, well, it is coming from this chip, I expect it to. So what else do TPMs do? They can do some crypto. They're very slow, so I wouldn't push my crypto there, but they can encrypt, decrypt, hash, create keys, sign, etc. And they provide secure storage in the form of non-volatile RAM and in the form of registers. And the registers are the ones I care about. So you can store in the TPM hashes, so SHA-1 or SHA-256 hashes of something, and we'll get to that. But then it stores them securely there, and later on you can retrieve these hashes from the secure storage. So TPM comes in different flavors. When I speak about TPM, I speak about the standard that's standardized by the Trusted Computing Group. But there's actually, many companies have their own, build your own TPM. So Google recently released OpenTitan, which is an open source implementation of their version of TPM. I think Microsoft has this project Cerberus, where that's their own version of TPM for cloud infrastructure. And Amazon has Nitro security chip, which is, again, it's a TPM. And finally, Apple has T2 chips in their devices. So people are using it, which is cool. I'm very happy about this. Then we come to measured boot. In here, the idea is that you boot and you run the CRTM, which is the core root of trust measurement. It's that first piece of code whose responsibility is to measure itself and measure the next component. So this is the root of our trust, if you will. So it'll measure itself, and instead of making a judgment on this measurement, it'll push it to the TPM. It'll say, hey, TPM, store this value. This is my value. And then it'll go and measure the firmware, which is the thing that's going to run next. Measure it, store it in the TPM. Hey, that's the firmware value. Then it lets the firmware run, which in turn will do the same process. It'll measure the bootloader, store the measurements in the TPM, and let it run. And then the bootloader will do the same for the kernel, measure, store, run. It's all good. The cool thing about measurements with the TPM is that you can't directly write to these registers I talked about. Whenever you want to put information in these registers, you have to do an extend operation. So you take the value you want to put in, and you tell the TPM, hey, put this value in. The TPM will read whatever is in the register already. It'll concatenate what you're telling it to write, hash this, and this hash is what gets actually stored. So when we store these measurements, we're effectively building this kind of chain of measurements, chain of trust. So it becomes very easy to detect if there's been some tampering, because if you do measurements in the wrong order or you measure the wrong things, your measurements will completely change and it'll be easy to detect. So another cool thing about measured boot is that when you boot, there's actually another standard by the TCG that it first tells you what you're going to measure into what register, but it also tells you to create a log. So every time you boot, you actually get a log of all the things you hashed, or some description of all the hashing or measuring events and what happened. And then this log you can use later to actually verify, okay, I have these measurements. You can rebuild the measurements and then get some information. So if something goes wrong, you can actually investigate where did the measurements go wrong. And that's a cool thing, but I'll get back to it. So this is what the registers look like. And I believe they're a bit more exciting to me than they are to you, because they're just a bunch of digits. But the first register is quite important. So register 0 is the core root of trust measurement that I spoke about. This is one of the important measurements of your system. It's the base of the trust in your system. Then we get things like the configuration of your firmware, then driver and application code for UEFI, secure boot policies. It measures a lot of things when it's booting. So that's kind of cool. And then you have kernel measurements in PCR 17 and 18. So once you got these measurements, there's two options. So with measured boot, you could have something similar to secure boot. It's called launch control policies. So you could define a policy that says, if you don't have these measurements, don't boot. But I don't like this forbidding machines to boot. I think it's nasty, and if something fails, I want to see it fail so I can actually figure out what went wrong. So I'm not a very big fan of just shutting down a machine when it fails, or rebooting it for that matter. So so what we do is that you can retrieve these measurements later on. So you let the machine boot normally. It'll boot. It doesn't matter if it's booting a good or a bad thing. What matters is that whatever you booted is going to be stored in the TPM, its measurements. And later on, you can use a quoting operation to retrieve these measurements. And quoting is just the process of telling the TPM, hey, can I please have these measurements? And TPM going, yeah, no problem, dude. Let me sign these for you, and here you go. So a quote is a little structure that has the information. So a tested value right there at the top is the actual summary of your system. So it's a hash over all the registers you're requesting. But then you get other nice information about your system, like a clock, the firmware version that your TPM is running, the number of times your machine has been rebooted, and this machine has been rebooted 2,000 times. It's a testing machine. And number of times it's been suspended and things like this. And this structure is signed by this key I talked about at the beginning that's unique to the TPM. So whenever you get measurements, you can check, well, it is the correct TPM. I expect to be sending measurements to me. They've signed it, so this is trustworthy. And you get this other extra information about the system that you can use to make some judgments about the trustworthiness of your system. So, for example, if the measurements are correct, they're good, but you see that every time you get measurements, your machine has been rebooted 30 times. It's like, well, hey, there is something else going on there. And then you can actually go and investigate to see if there's something else wrong. So that's pretty cool. And then the process we use to judge whether a machine is trustworthy or not is called remote attestation. So you set up an attestation server, which is a server that contains a database of all the good values that you would expect in the machine. So for this to work, you build a reference machine running all the hardware, software, firmware that you want and you expect. And then you take those measurements, store them in this good values database. Later on, during the life cycle of this machine, you can have a challenger ask, hey, I want to know if server A right here is trusted. Can you go and check that for me? Then the attestation server can communicate. It can request the measurements via this quote operation, return it, verify that the measurements are good or bad, and then issue a statement, yes, A is trusted, it has all the measurements we expect it to. So that's about it. So with secure and measured boot, I don't want to preach one over the other because this is not what it's about. It's more like they're complementary technologies. I would be very happy if you could kind of have both of them. So there's some trade-offs. So in secure boot, you are stopping unauthorized components. And again, it's going to depend on your use case, if that's what you want to do or not. I'm not a very big fan. I'm for detecting what is going on in your machine. So I like the fact that measurements let you investigate what went wrong when something goes wrong. But I have to admit that maybe in a situation with consumer laptops, you might not want to worry about the whole infrastructure of setting up good values and so on. So you might want to use secure boot. That's fair enough. And then, yeah, in one of them, you're hashing and comparing these measurements, and the other one, you are just verifying signatures. So I like the trust, but verify. Look at those measurements. So a bit of a different perspective. So far, we've been talking about x86 machines, and that's mostly because I do my research on x86 machines. But I thought it was worth it to bring a different perspective from ARM. So if we have a Raspberry Pi, I'm going to go through the boot sequence for a Raspberry Pi. And as a disclaimer, I'm not going to go into it in too much detail, because if you want to know more about trusting Raspberry Pis, you should stay here for the next lecture that my colleague is giving. This shameless plug right here. Anyway, back to my talk. When you boot a Raspberry Pi, one of the different things is that you don't start using the CPU until quite late in the boot process. So you power on your Pi, you plug in the cable, and it starts doing things. So it first runs the first stage bootloader, which is programmed in read-only memory during manufacture time. And it's running in one little core in the GPU. And its responsibility is to find the second stage bootloader, bootcode.bin, which is the code that will actually load all the firmware for the GPU so that the GPU can fully power on and start working. Then the GPU firmware runs, and it sets up the CPU to actually take instructions and start working, and it decides where am I booting from. Well, that's usually the SD card. And then after this start.elf runs, execution is transferred to the CPU, and then you start looking for your kernel image, usually a Linux kernel, but you can run some bare bones applications or some other bootloader. So, well, the thing I want to highlight here is that an x86 you start running from the CPU from moment one. But ARM have a different approach to it, where they utilize the GPU and don't worry about the CPU until quite late, which is interesting. So they have, as far as I understand, two different types of devices. So they have the Cortex-A kind of processors that are meant for big devices, a Raspberry Pi, because of course ARM is more into this embedded world, so Pis are actually quite big in this context. So these are the kinds of processors that would go into a Raspberry Pi, a phone, things like this. And then they have the Cortex-M family, which are the things that would go into a light bulb, a flooding detection sensor, these very, very tiny resource-constrained things. So since they work with this, it's a different industry. Intel try to make these general-purpose things and architectures, whereas maybe ARM is more focused on tiny little things and embedded things. So they actually have a concept of instead of trying to secure boot your way through the whole platform, they actually divide it into the trusted world, which is this green, very pretty one here, and the non-trusted world. And, well, I don't really want to go into the details of how these things work, but they do some sort of secure boot in the trusted world, which means you can trust anything that's there. We minimize the code that you need to trust, and you make it critical. And that runs in this partition. It's isolated from everything else. And then you have the non-trusted world. And that's a scary image, but non-trusted doesn't mean malware-infested world. It just means these applications are not relevant. You don't need to trust them. So it doesn't mean untrusted. It just means you're not making a judgment on them because you're isolating the things you actually want to trust. So, and then they have a secure monitor, so a middleman that will do the transfer between the two worlds and maybe move the information around. So it's a different concept. I think it's interesting. It might work better in these resource-constrained devices. It might make sense to actually minimize the amount of things you want to trust and then verify these. So there's still one problem, though. Where does your firmware come from? Does anyone know here? Raise your hand if you know exactly where your firmware has come from. Yeah, not my colleague. Okay, somewhere over there. Anyway, it usually goes so that the firmware supplier, they have this big piece of code, which is the firmware that can do all the things. And then they ship that to the OEM, who may add more firmware. It might disable some features, enable some other features. They modify it in whatever way they see fit. They flash it on the device, and then this device is shipped off to the customer. So that's all very well, but then I noticed during the testing, this is one of our testing machines, and I was very happy. Look at how many hashes I have in those PCRs. Oh, these measurements are so great. Until I actually started looking at it very detailedly, and I noticed, wait a second, these measurements are all the same. Wait, that's not correct. So after a lot of time, because it took a lot of time to try to figure out why these things went wrong, I went and I read this PC firmware client specification made by the TCG, which is a very long document, and I'm surprised I didn't die of boredom. But anyway, after reading through that, I figured out that, hey, I can go and check the logs, which is a whole different story. So the platform firmware specification says, whenever you boot, you have to measure things and you must store an event in the boot event log. All good, that happens. But there's also in the UEFI specification, when you exit boot, this log gets trashed. So it's, yeah, your log is being written to, but it's also getting trashed before you can actually see it. So that was a bit complicated. Nowadays you can get that boot log. So starting from the Linux kernel, was it 5 point something? I can't remember. They introduced a fix that will actually pass on the boot log so that you can have the boot log available in Security FS during runtime, which is pretty cool. But you only have it in some distros. So in the distros I'm testing, you have it in Fedora because they follow the upstream kernel very nicely, and they actually update it, and they have this feature. But I actually have Ubuntu on my machine, and they don't do that. They don't have that feature there. So in my machine, I can't see the log. In some of my test machines, I can see the logs, which is quite interesting. But I like these logs because then, as I said in the introduction, I focus on root cause analysis of trusted computing systems. So when something goes wrong, which happens because in the wild there's updates, things change, it's bound to happen. When you see measurements change, I like the fact that you can go to the log and actually see, well, what did I measure? But when I went to this log, it was a bit depressing. There is this kind of event. It's the EV separator event. And this is the event that you have to put in the log and extend to the TPM once you pass control from the firmware to the bootloader. So it indicates where the events that come from firmware end and the events that come from the bootloader start. But the thing is, this was the only event I had for this PCR. So it turns out the firmware in that machine wasn't actually measuring anything, which was baffling for me. It was like, well, but I read the standard. The standard says you must measure this. But it's not happening. And well, my theory is that people are not really aware. Well, some people are not really aware that these things happen, that these are features you can have enabled. If you actually go and read the spec, you can measure so many things. You can measure what exact piece of memory you have and what firmware it's running. It can go very detailed, but nobody's asking for it. So it doesn't get implemented. You implement the bare minimum, you're compliant, you go on. And well, sometimes not even the bare minimum. So I do this because I like to raise awareness. I would like to see people using this. It makes me sad that I noticed this and I can't actually go and check what is my firmware doing because I have no control over my firmware. It gets updated, somebody sends it, well, it's signed probably, but I can't read the code. And well, I'm not a firmware developer, so I'm not sure if I exactly would know how to read the code. But the point is that it makes me sad that we don't really know. There's not this transparency. We don't really know what the firmware is doing. So this is technology that could very well work to our advantage. But there's no demand, so it's kind of mediocre at this point in that sense. So I hope it gets better. And it actually makes me really happy to see that there is some movement towards open source firmware. So in my hopeful mind, I would like to think this is kind of like when Linux was starting, and now it's super mainstream and everyone uses open source Linux. Maybe we're going to move to open source firmware. There's projects like Core Boot and Linux Boot, which are this. It's the same mentality as I have. Well, they actually don't want very bloated firmware. They want to minimize the things that firmware does and then move it over. But I gotta admit, I mean, at least UEFI is trying. So they have this, the UEFI forum have this EDK2, which is the open source reference implementation of UEFI. So they have something. The problem is that then everyone takes it and starts disabling some of the things and modifying it. So I would like to see more of this moving towards open source firmware. I think that would be pretty cool then, because you can't protect. If you don't know what's happening in the machine, can you really protect it? So if you take anything from this lecture is there's different kinds of boots. People do it differently. I hope for a more open world, and I want us to benefit from this technology. So this is my presentation. Thanks for listening, and if you have any questions, I think we have some time for them. Thank you.
Thank you, Gabriela. So thank you, Gabriela. Do we have any questions? Okay, can you come closer here, and Karolina will give you a microphone.
Oh, should I be scared? You're very eager. This is the first time I've had very eager people wanting to ask questions. Okay.
Okay, hi. So maybe a short question. Could you be able to show us some demo of reading how to actually, in practice, obtain these logs from the secure boot process? Are you prepared to show us some distro how it actually looks in practice? Because I'm really interested in this.
I could, but as it happens when you travel abroad, when I tried connecting to the VPN to the company, my machine went down. So I would love to show you a demo. I actually have it, but right now I can show you a very badly parsed log. So if you're interested, of course, let's meet afterwards.
Asking a quick question, it's actually about Apple, because this gets interesting because they, since 2016, of course, implemented T2 security chips on their Macs. And actually, do you know that if they do open this information about secure boot process or log them? Because I did a quick Google check and couldn't find really anything. How can a user actually do and verify this information? Because you mentioned that we should trust, but we should also verify. So
Yeah.
can we do it on Apple platforms, or they locked it in completely? Do you do research about this side of the IT world?
Yeah, so I haven't tested in Apple machines, but I know that they do some form of secure boot. So I think with Apple you can get this verification, but I don't know if you can actually get the measurements and the log, because I think they're just verifying signatures. So as far as I know, that's how it works.
Okay, on most ARM platforms, we usually have some preloader burnt inside the chip. But on x86, usually the first code that is loaded, it's usually comes from an external chip. Do you know if the implementations on modern x86 platforms actually measure the code that is loaded from external flash and then run this measured code, or maybe they do reread the code from the flash again after the measuring? My point is that it could be relatively easy to perform a time of check and time of use attack to subvert the TPM. Maybe the situation has changed recently. It would be nice if you could elaborate a bit on this.
Yeah, so as far as I know, Intel have this thing called boot guard, where they will verify this first initial building block, so the very first little piece of code that comes from Flash, and they'll verify signatures, and that is their root of trust. If you have a physical TPM, you can directly store measurements in there and use this for verification, so you could measure it. I know that there is one black hat presentation on this time of use, time of creation attacks. I would encourage you to search for it, but this is on platforms using only secure boot, which does the signature verification. So if you have the discrete chip on board, you can send the information over and you can measure it and verify it. So I think the attack is valid when you're only doing this verifying signatures that come from your firmware anywhere, because you're not using any external security module for it, as far as I understand.
Okay, thanks.
Hi. Thank you for this very interesting talk. First question, you showed that in the UEFI specification, they are actually demanding to trash the log, this boot log.
Yeah.
Is there like a security justification for doing so, a reasonable one?
Not that I can find. I think it's just written that there's this function that you call when you finish booting up, so when you hand over the control to the kernel, which is called some exit boot services. And I think it just happens to be part of the UEFI stuff that gets trashed, so it's not stored in any UEFI variables that you export later during runtime to the system. I think this is changing, but at least right now it's like that. There's workarounds to get
And
this.
second question, you showed that actually every big player implements their own TPM. So does this mean that they think, oh, we are so good, we can do it better than the others? Or does this mean, oh, we actually don't trust the others to implement it, and so we only trust ourselves?
Not necessarily. So I think there might be supply chain considerations here. So I think it's important if you have a big control, or if you can have control over your supply chain, you actually want to bring that in. For example, Cisco has their own version of TPM. And the reason why they have their own version of TPM, it's because they modify the chip so that they add an extra identity UID in there. Because, well, after the NSA attack I mentioned, they thought, well, we can't go on like this. We need to verify. So I think they use a TPM standard, but they adapt it to their use case. So in their use case, they need an extra UID there.
So you think it's mostly for extra things?
Yeah, I think it's
and
mostly for extra
not
things.
because one doesn't trust the other?
No, I think it's for extra things and supply chain considerations. So